Hello, everyone. This is Qixin Wang from the Hong Kong Polytechnic University. Today, I'm going to present my collaborative work with my students and colleagues on test oracle for reinforcement learning software based on Lyapunov stability control theory. As we all know, reinforcement learning has become more and more important due to its ability to train controllers for complex systems and robots. Particularly those complex systems and robots that are hard to be analyzed using conventional control theories. The typical framework of reinforcement learning has two parts. One is the environment, intuitively the physical plant being controlled. It takes as input the action, aka the actuation from the controller. And then its state will evolve accordingly. Typically, there is an interpreter continuously monitoring the state of the environment, and then also judge the current state of the environment as well as the current action input to the environment. The judgment output is called the reward. The other part of the reinforcement learning framework is the reinforcement learning program. It takes as input the state and the reward coming from the environment to train an agent, aka the controller. The agent, aka the controller, is in charge of generating the actuations, aka the actions, to be applied to the environment. So at a higher level, the ultimate output of the reinforcement program is the agent. And the ultimate input to the reinforcement program is the environment. Very often, the physical environment is also replaced by a simulator, aka the digital twin of the environment. So the environment part can go entirely cyber. So this will allow millions of times of training or testing without wearing down the physical plant. As the reinforcement learning generated controllers being used for more and more safety critical or mission critical control robotic applications such as surgery, smart driving, or nursing, ensuring the correctness of the reinforcement learning programs becomes more important. That means we need to carry out testings and debuggings on the reinforcement learning programs. For testing and debugging, one indispensable tool is called the oracle. That is a piece of tool that can judge a piece of program, whether or not it is buggy or not, based on the input and output of the program. The oracle is well known to be difficult to design, even for conventional software. For reinforcement learning, actually, as well as other learning programs, the oracle design becomes even more difficult. This is because for learning, reinforcement learning included, the legitimate output of the learning is often not unique. For example, suppose we want the reinforcement learning to learn a controller to operate a quadcopter to fly from point A to point B. There are multiple ways to fly it, and all of them can be legitimate. For example, the way to fly it through this dotted line of trajectory and through this dashed line of trajectory. Which one is correct? Which one is wrong? It's very hard to say. Okay? Some controllers may result in less overshoot. Some controllers may result in less time cost. Some controllers may result in less jitter. All of them can be legitimate. So it is hard to judge whether or not the output, that is the controller, from the reinforcement learning, whether or not these controllers are correct or wrong. So how to design oracles for reinforcement learning, this becomes a very big challenge. To address this challenge, our philosophy is that we need to go back to the roots, the control domain theories. In fact, in the well-established conventional control theories, there are many non-trivial controller design problems with very well-established solutions. These solutions can be analytical, can be numerical, and these solutions have their features. So our conjecture is that if the reinforcement learning program is bugless, then its generated controllers should most often agree with the well-known solutions features. So this is our solution heuristic. Particularly, we look at a very well-established controller design problem called the Lyapunov stable controller design theories, or Lyapunov stable controller design problems. For this kind of problem, the context is that we're given a linear dynamic system describable by this linear differential equation set. Okay, so in this linear differential equation set, we have X is a n-dimensional vector describing the state of the plant, that is the environment, the physical environment. U is an m-dimensional vector describing the control actuations. And the dynamics of the states, how the state will evolve, that is the time derivative of X, is determined by the current state and the current control input, control actuation, linearly. Here, both A and B are constant coefficient matrices. So this is a linear relationship. So this is the context. And the demand is that we want a linear controller, which means U is linearly related to X. K is also a constant coefficient matrix. We demand a linear controller that will guarantee the holistic system is stable in the sense of Lyapunov. So what is stable in the sense of Lyapunov? Basically, it means that in the n-dimensional state space, there should be a region. Typically, it's a hyper-ellipsoid. And starting from any point inside of this region, the future trajectory of the state X will never exceed this region. Okay, so this is what we call stable in the sense of Lyapunov. For this kind of demand, we have very well established solutions to find the wanted linear controller that is stable in the Lyapunov sense. The key to the solution is to first construct a hidden function called the Lyapunov potential energy function. It is a function of the state X. So once we have constructed this function, then we can easily find the linear controller that is stable in the sense of Lyapunov. And then the feature of this solution is that the so-called controller U always decreases the Planck's Lyapunov potential energy over time, as this diagram shows. So here we are assuming that the state space is two-dimensional, X is two-dimensional. And then upon this two-dimensional state space, the typical Lyapunov potential energy is this bowl-shaped surface. And then starting from any initial state, we have an initial Lyapunov potential energy value. And over the time, this potential energy is always decreasing. As long as, because of this feature, the trajectory of the state is always confined by the circle here. So this is a very well-known established theory in control. So exploiting this theory, we propose our oracles. We conjecture a correct IL program can always figure out the hidden Lyapunov potential energy concept and the energy decreasing feature. So the specific steps is like following. First, we create many non-trivial Lyapunov stable controller design problems. This is easy. Just randomly generate the A matrix and B matrix. Every pair of A, B correspond to a problem. And then we use the conventional method to prepare the ground truths Lyapunov stable controller U and the Lyapunov potential energy V as per the conventional numerical solution. We get the U and V. And then during the reinforcement learning training stage, we use the ground truth Lyapunov potential energy V decreasing feature to stimulate the reinforcement learning program to guide the reward generation. And we conjecture that if the reinforcement learning program is bugless, it should be smart enough to figure out the hidden Lyapunov potential energy concept, and then should always guarantee the Lyapunov potential energy is always decreasing. So in the test stage, we will check if the reinforcement learning generated controller complies with the ground truth Lyapunov potential energy decreasing feature. So specifically, an RL generated controller is complying if and only if we consider it complying, okay? If and only if over Vi theta percentage of its tested control steps are Lyapunov potential energy decreasing. And the reinforcement learning program is considered bugless if and only if over theta percentage of its generated controllers are complying. So this kind of proposal, this kind of oracle, we call it the Lyapunov potential energy abnormality oracle, or LiPA oracle. So it has two configurable parameters, Va theta and theta. So how to judge? To judge the efficiency of the effectiveness of the LiPA oracle, we carry out empirical evaluations. So we choose a very well-known open source reinforcement learning program repository, the stable baselines. And then from this stable baseline repository, we select representative implementations of classic reinforcement learning algorithms, including A2C, PPO, TD3. And this becomes our bugless reinforcement learning program benchmark. And then we inject bugs onto this benchmark to create the buggy reinforcement learning program benchmark. The injected bugs coming from both the artificial bugs constructed according to the surveys on typical reinforcement learning software bugs, and also from the real world bug listed in the stable baseline Git repository. Then we threw both these bugless and buggy RL programs to our oracle, LiPA oracle. And to compare, we also threw these benchmark programs to human oracle. Basically, is a committee of human experts. And we compare the labeling of buggy and bugless. And this is the raw results. It's not very visual. The visual is here. So the x-axis is various kinds of oracles. HO means the human oracle. And then the LiPA oracle, we have different configurations depending on the Va theta and theta values. Different colors of columns means accuracy, precision, recall, F1 score. So we can see that the majority of the LiPA oracles, they can outperform the human oracle in many cases. Particularly the LiPA Va theta equals 100% and theta equals 75% oracle significantly outperforms the human oracle in accuracy, precision, recall, and F1 score. So is in the evaluation for false positive rate, false negative rate, true positive rate, true negative rate, as well as in the ROC curves. So our conclusion is that the LiPA oracles outperform the human oracle in most of the metrics, particularly the LiPA Va theta equals 100%, theta equals 75% outperforms human oracle significantly. These are the data on various metrics. Thank you.